video, we're going to look at the forward pass of the transformer. And the transformer that we are looking at today is the decoder only transformer. It's not the encoder only transformer, right? Or it is neither the encoder decoder transformer. So when we first hear the word a transformer, so we should know that there are three types of transformer. Encoder only transformer. Think about a transformer like BERT, bidirectional encoder representation of transformers, right? Encoder-only transformers are not generative in nature. They produce embeddings. The input is largely the same to all of these transformers. The input is large amount of text at training time also and at inference time also, right? But the use cases are completely different. For encoder-only transformer, whenever you think about the GPT family, GPT-1, GPT-2, GPT-3, all of these are decoder-only transformers, right? They are generative in nature. They are trying to do the next token prediction portion. This is nothing but the inference time. So let's say let's just imagine that we are simply generating the next token. For this particular video, we will assume that one character is one token, right? It says that the characters that we have written is 12. That means we have 12 tokens here. H is a token. H is represented as this particular vector in this particular dimension. So it's a 64 dimensional vector. Similarly, E itself is a token, L again is a token, O token, right? Space is a token, W is a token, R, O. All of these characters in itself are tokens. This decoder stack is first doing something which is known as attention, right? We're calling it multi-head attention. We are also calling it self-attention. Then there is also masking that goes on in the attention block. But pass, then we again do normalize, and then there we have one more linear layer, or let's say rather the output head, and then on top of it we have applied softmax distribution function to produce probabilities. From these probabilities we will be able to sample, from this probability distribution we will be able to sample the next token. Query, key and value are matrices. Q is being produced once we multiply once we multiply the input with WQ, right? X gets multiplied with WQ, X gets multiplied with WK, X gets multiplied with WP. Then we produce query, key and value. Query, the abstract idea behind query is, what am I looking for? The idea of key says, what do I have that other people are looking for? What patterns do I offer to other people, or basically to other tokens, not to other people but to other tokens? Value, what content do I have? So after attention, every token passes through a two-layer neural network. So the feed-forward neural network architecture is completely the same. Input layer, which takes 64 dimensions, and it's going to expand or extrapolate it into 256 dimensions, right? So that means the next hidden layer is going to be in 256 dimensions, and then it is again going to project it to 64 dimensions. After all of these four blocks, we will be able to pass the output through the softmax. The softmax is going to apply softmax function on the 64 neurons that were part of the feed forward neural network, and every neuron will be assigned a probability, right? And the probability should sum up to 1. So before we were introduced to all the GPT-5 and the current best of the best models, we had something known as the BERT era. It was the pre-GPT-3 era. We have seen a GPT-2, a decoder-only transformer, very simple. We've also seen it in very detail, especially the architecture in the last video. So this video, we're going to go in a chronological order and discuss what was the BERT era, the pre-GPT-3 era. Transformers became very famous in the whole natural language processing domain. Why did they become famous? Because recurrence was being replaced by the idea of attention. One breakthrough or one good paradigm shift that happened was the idea of unsupervised pre-training, right? So what we used to do, we used to train a very large model, especially during the time of BERT. We used to train a very large model on enormous amount of text, right? So it was self-supervised training and unsupervised training. So we did masked language modeling. We used to take that pre-trained model and then attached a task-specific output head, right? Or a domain-specific output head, which basically introduced the notion of fine-tuning. But we still needed the labeled data set. So it was like, it's good to have a large base model, it's good to have a large brain, but whenever you want to do something important, something useful, like maybe simulate question and answers, we need QA pairs of labeled data set. Let's say we want to do sentiment analysis, we will use BERT to produce representations, but we would still need a labeled data set of sentiments, right? So this was the paradigm. There was a big need of labeled data set and BERT was also being used to produce large linguistic representation from raw text, right? Then the GPT-3 paper introduced couple of things that kind of helped engineers, look at scaling laws, look at power laws, and look at the idea of in context law. So since we are talking about the GPT-3 era, or we are trying to come or arrive into the GPT-3 era, we were introduced with the idea of in-context learning. So at the surface level, it looks very simple, right? So you give the model a prompt, and let's say the model, you're trying to give the model a prompt. For example, translate English to French, right? So you're giving it a couple of examples. Let's say you're saying that cat will translate into chat and dog will translate into chin, and what is house, right? So but what exactly is happening here? The model's weights are not changing in this few short learning. Whenever we talk about learning, we always have this notion of parameter based learning, where we are updating the parameters. Here we are not changing the parameters. The model is just computing the forward pass. The model is never computing the backward pass. Why? Because we're standing at the inference time. We instruct the model with a few examples. What's happening is there is no gradient descent, there is no backpropagation, there is no optimizer, there is no Adams optimizer, no training loop, nothing. But the behavior of the model is still changing based on the examples in the prompt. So where is the learning happening, right? So that's why we call this idea as in context learning or implicit conditioning. So whenever we are including these instructions or examples in the prompt, we are not updating all the parameters. What we are essentially doing, we are just altering the current context. That's it. So the prompt is becoming the part of the model's input size. It's going through the model. It is helping us compute the forward pass, right? So we're nudging the model to compute an internal representation in this representation space, in the forward pass space, and we are giving it a few examples to produce this representation. One shot means you only give one example, zero shot means you give no examples, right? So that's how you should remember it. Zero shot, zero examples, one shot, one example, few shot, few examples, let's say 3 to 10 examples, right? Everything that you're giving is part of the weights, right? That's why there is no updation of parameters. That's why parameters are completely agnostic. We don't care, right? And the larger the model, larger and heavier the model, like GPT-3, better is the performance, even within context learning. So the in-context window, or the context window during the in-context learning, was acting as a working memory for the model, right? That's why the forward pass was able to produce a better representation during your inference stage. Prompt can help you achieve your particular task if you provide few demonstrations or few examples, which is nothing but few short learners. That's why the GPT-3 paper produced something which was called as language models are few short learners, right? So why this becomes a bridge to GPT-3? Because before GPT-3, we thought that generalization required supervised fine tuning, and we have to fine tune for all the domain specific use cases for generalization, and we need to have labeled data sets always for every particular useful task, right? But in context learning simply suggested that if your model is large enough, if it has learned the overall representation of the world, of the internet, over raw text, it has its prior ready over the language, you can trigger its posterior, or you can better its posterior probability by providing a few short examples in the prompt itself, right? So this is what GPT-3 paper demonstrated. And this is, a GPT-3 paper did not demonstrate this by just a hypothesis. They produced series of examples, right, as evidence on how the performance got better with scaling the model, and with the idea of a few short learner, or with the idea of providing a few short examples and zero shot examples. So it compared against a lot of data and against a lot of domain specific tasks.